So this is 7-5 solving radical equations. And for VIX, you want to remember that radicals and exponents are inverses of each other. When you have a square root and a square, they undo each other. They cancel each other out to become just x. A cube root and a cube, they undo each other to become just x. So we also need to remember that for any even power root, so a square root, a fourth root, a sixth root, that there are restrictions on the domain. So your question might say, solve the following equation, check for extraneous solutions, and state the domain. So if you have the square root of 3k minus 1 equals 4 as your original problem, you want to make sure that we need to get rid of this square root. So in order to undo a square root, we square it. But whatever you do to one side, you have to do to the other. So we square both sides. That cancels out the square root with the square, and you're left with 3k minus 1 equals 4 squared is 16. Add 1, divide by 3. So you get that k is equal to 17/3, which is your final answer. However, because it's a square root, you have to be super careful that you don't have a negative value underneath the radical. So in order to help us with this, we need to talk about our restrictions. Your restrictions are setting whatever is underneath the radical greater than or equal to 0. And we're going to do this to find the domain. The domain is essentially your restrictions. So this value here, this 3 expression, 3k minus 1 is greater than or equal to 0, is then solved. So you add 1, divide by 3. So k has to be greater than or equal to 1/3. Our answer of 17/3 is greater than 1/3, so we're good to go. When we check our solution, we have to note that this could potentially be an extraneous solution. So 3 times 17/3, the 3's cancel. So I'm left with 17 minus 1. Well, the square root of 17 minus 1 is 16. Square root of 16 is 4, and 4 is equal to 4, so that works. Here's a different type of example where you might need to solve. So when solving, this time there's a square root on both sides. Well, again, to undo a square root, you square it. That's the inverse operation. When solving, you can set, now that they undo the radicals, each is set equal to each other. So 3x minus 7 is equal to 5x minus 15. We subtract the 3x to be 2x. We would add 15, so we get 8. 8 is equal to 2x. Divide both sides by 2. X is equal to 4. Again, you need to make sure that this is working within your individual radicals and part of your restrictions. So our restrictions is this has to be greater than or equal to 0. But because we have another radical over here, we have to do the same. So 5x minus 15 has to be greater than or equal to 0. So solving each one out, I add 7. So 3x is greater than or equal to 7. Divide by 3, so x is greater than or equal to 7/3. Here we would add 15. So 5x is greater than or equal to 15. Divide by 5, x is greater than or equal to 3. Because we have two different restrictions, you have to go with the one that is more restrictive. So 7/3 is less than 3. So 3 is more restrictive than the 7/3 are. So x has to be greater than or equal to 3, in which case 4 is. So 4 works. If you substitute that back in, 3 times 4 is 12, minus 7 is 5. This would be the square root of 5. And 5 times 4 is 20, minus 15 is 5. So the square root of 5 equals the square root of 5. That works too. Here we have the cube root of 2x plus 11 equals 3. However, we don't need to worry about restrictions because you can have a negative value underneath the radical for a cube root, a fifth root, a seventh root, anything odd. It just can't be, we have to state our restrictions if it's even. So because there's no restrictions, we can go through and solve. And because it's a cube root, we want the inverse operations, which is going to be the cubit. So the cube root and the cube undo each other, and you're left with 2x plus 11, and you have to do the same to both sides. So 3 cubed is 27. Subtracting 11, you get 16. Dividing by 2, you get 8. Substituting this back in, 2 times 8 is 16, plus 11 is 27. The cube root of 27 is 3.